population. And so for person 1, beta TT could be minus 0.07. For person 2, beta TT could be minus 0.04. For another person, it could be minus 0.08. So what we are saying here is it's actually not constant across the population, but to achieve this without a lot of complexity is very hard, right? So if I don't have enough data for each person, I cannot estimate this for each person because I only have one record per person. I can only get an average across all of the population based records. So what we do is we make an interesting assumption. What we do is we'll say, let's assume that travel time is actually a distribution. The coefficient itself follows a distribution. Okay. Now, if you think of it as a distribution, what that means is different people lie on different parts of the distribution. So if this is the mean, minus 0.05, there are people here, there are people here who are even more sensitive to travel time. There are people here, there are people here, there are people here who are less sensitive to travel time. So this allows for additional flexibility on how travel time can impact the choice process. Okay. Now you can think of the same way for travel time, travel cost, any variable we can do the same. So this, but to estimate this distribution, it might be challenging. So, but what we do is we'll assume that this distribution follows a normal distribution. If it follows a normal distribution, I can define a normal distribution with two parameters. All I need is two parameters. So I have the mean and standard deviation or variance. Okay, if I get, so now instead of estimating one mean parameter, which is what I was doing in an MNL model, what I'll do now is I will estimate the mean and the standard deviation of this mean. So that will tell me how variable that coefficient is across the population. So if you don't do the standard deviation, this is what is called a point estimate, right? Because we're estimating 1 point for everybody in the population. So now we can relax that assumption and estimate the overall distribution across the population. Now a challenge with that is, okay, it's all great. We have a distribution, there is a mean and a standard deviation. But what do you take as a parameter for each person? Okay. So in MNL probability computation, what we do is we use beta TT to compute the probability. Each time you are estimating the model, each iteration probability is computed for maximization process. For that, we need to use the parameter. So now in this case, because it's a distribution, I have to take realizations from the distribution. So person 1, I don't know where that person 1 is on this distribution. He could be here, he or she could be here, 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 here. So what we need to do is we need to evaluate the probability on different parts of the curve. Okay. So I'll assume this person is here, this person is here, this person is here, this person is here, this person is here. So I'm showing you 10 realizations. So we compute 10 coefficients. So first one could be around the mean, 0.05. To the left of mean, to the right of mean, left of mean, and so on. So for each of these betas, we compute the probability. And then once we have run enough number of realizations, we take the average of the probability to get an estimate for one person. Okay. So basically what I'm doing is, because this is the distribution, I have to integrate out the area under the curve to get the probability. So that's what I'm doing here. So we do this using what is called pseudo Monte Carlo approaches or quasi Monte Carlo approaches. So what happens is, when you're doing an MNL model, for each person, you are computing probability once in the computation of the log likelihood function. But when you are here, for each person, you compute the probability at maybe 100 points or 200 points. So we are doing, if you have n records, in a multinomial logit model, you are only doing n probability computations. But if you're doing an mixed MNL model, you're actually doing n times 100 evaluations of the probability, because we are averaging it over 100. Sometimes we might need to do even more to get stability, but usually it's 100 to 300 is the range at which you do this. So that's why this increases computational complexity, because if it takes 1 minute to run here, it'll probably take 15 minutes to run, because you have to compute multiple evaluations of the probability. This is for one iteration. For each iteration, it increases the load 100 times. So when you run 100 iterations, the overall runtime can increase substantially fast. But it gives, now with all the computational power we have, even mixed logit models run in like 3 or 4 minutes in general, unless you have very large data sets. So it has become very practical to use mixed logit models. Okay. Any questions? Okay. So there are two ways of capturing the correlations or unobserved heterogeneity in a mixed logit model. One of them is called error variance, and the other one is called random parameters. So we'll start with the random parameters because we already are talking about it. So let's say utility for drive is beta naught, beta tt, tt drive plus beta tc, tc drive. So let's say we have this utility. So what we can do is, what we can say is, this is no longer fixed. So in that case, we'll write it as beta is a distribution. So it will have two components. There is a beta and there is a sigma. Okay. So beta will be a realization that follows an distribution from these two. So now I can do the same for my beta tc also with two components. So what I'm doing is I'm allowing my parameter to be random across observations. So that's why this formulation is called an RP model or a random parameter model. Okay. Now in the second system, we don't worry about variation arising from independent variables, but we have epsilon. This is split. So we split the errors into multiple parts and say transit and drive have a correlation. Transit or different transit alternatives. Just like what we did in the nested logit, you can capture error correlations there. So what that means is, if you have 5 alternatives, maybe alternative 1 and 3 are correlated. So let's say alternative 1 is walk, alternative 3 is bike. Both are non-motorized modes, so there can be a correlation between those two. Let's say alternative 2 is metro, alternative 4 is bus. Again, those are public transit alternatives, so there can be correlation. So we can capture correlations across the unobserved parts. Okay, so epsilon will split, just like we did in nested logit. We split the error into multiple parts and say there are some common parts and some independent parts, and we can capture that. Again, that also will follow the same structure for simulation, for estimation using pseudo Monte Carlo or quasi Monte Carlo methods, and then the probabilities will have to be computed multiple times to arrive at your valuation. So with the emergence of error variance models, it's actually very easy to capture correlations across alternatives in a mixed logit model, even compared to nested logit. In a nested logit model, there are strict rules. There has to be a strict hierarchy. There has to be the theta has to be less than 1, and if there is eta and theta, eta has to be less than theta. There are strict constraints like that. Here we don't have any constraints like that. You can actually add error correlations in a more flexible fashion. And there's a paper by Kenneth Train which shows that a mixed logit model can approximate any nested logit model that you can estimate, any nested or cross nested or any form of models that you can estimate. The only advantage of nested logit models or variants of that is their closed form probability expression. So here we have to do integration. There we don't do any integration. In a nested logit model, there is a formula. Yes, the formula is not simple or easy, but still it's a formula. If you code it, it's an analytical formula. Analytical systems are always better than simulated systems at some level. For that reason, people still use them, but you can approximate any reasonable nesting structure with a mixed logit model, and it becomes easy to run those models. So I have some. So in the probability structure would look like this, where you have an integral evaluated over the distributional assumption. So I talked about how we can use coefficient of travel time as a normal random variable, but there is a case to say that travel time should always, the coefficient of travel time should always be negative. So if you take a normal distribution, we are allowing for some probability for the coefficient of travel time to be positive. Okay, so we can avoid that by using log normal distributions, a negative log normal distribution or a truncated normal distribution. So all of these are possible. It's just that some of them it'll get a little complicated in the estimation process, and the functions are not as smooth with other distributions. If it's a normal distribution, estimation is easier and stable. But if you use log normal or a truncated normal distribution, the estimation process is not as stable, and you can run into convergence issues. So the model will keep trying to estimate the model, but it will not converge to a solution. Okay. Yeah. No need, because we are estimating only one extra parameter for each variable. So if you think about travel time, with the data set we estimated usually beta travel time, but now we are estimating only standard deviation, just one more parameter. So we still can do it with the same data that you have, but yes, the larger the data, the better you will get, better estimates you will get. Also, if you have multiple repetitions, it will look even better. Yeah. Yes, different choices for the same person if available. Again, it's not a requirement. If it's there, that'll be that's what is called panel data, and that will increase the advantage of using these methods. Yeah. 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 So when we are doing the latent segmentation model, I think that's what you're referring to. There is every record in your data set goes into that segment, even into that sample. Every record. The only thing is we weigh. So if let's say there are three segments. Okay. So each person 3 segments, but their output from there is not directly add, right? That will make it 3 people, right? It's not 3 people, it's only one person going through all three of them. So we put a weight for each person for each segment. So I behave 13% like a person in segment 1, 70% like a person in segment 2, and the remaining as a person in segment. So there are those weights that reflect your choice. So the weights will take care of them. So when the model is estimated for that segment, everybody is used in the estimation of that segment. But I only take of their choice, because I'm weighing the choice with them. Okay. There should be adequate number of records in each group. Okay. In the if you're exclusively allocating people to a segment, if you are you splitting the data based on age, then you are splitting it. So if there are 20 people in segment sample age group under 25, you only have 20 people. That's it.
It's the overall population. I need to say, for example, we can say overall 10 lakh population. The saturation you get right to the sample requirement is saturated at 4. And among those, if you want to feel the 20% segment, I think we might be very less sample. That is, like take 400 from every age group, or
so it is if you have to separate that out, you I don't want to say everything has to be 400. If 400 is what is, but at least 50 to 100 should be there in each group. Otherwise, the quality of the estimate will not be that good. So this is the error component formulation where I'm writing the coefficient gamma y is the beta, the coefficient, the psi qi are the error. So I can formulate them in this fashion. So basically what we are doing here is we're introducing what is called heteroscedasticity and correlation. So depending on how we use the C variable there, you can introduce correlation between different alternatives. So you can do one correlation between 1, 2, 3, 4, and 5, or 1, 2 only, 1 and 3, 2 and 3, 2 and 4. All of these can be accommodated by just how you decide. So this is how the matrix structure works here. For example, what I'm showing here is, if you look at, this is error 1, error 2, and error 3. If you look at this column, error 1 and error 3 have a common correlation. Error 2 has an independent part. Error 3 also has an independent part. So this column, there is no other correlation there. This column is also there is no other correlation. So I am capturing error variation and also common correlation between 1 and 3. So it simply boils down to how we define our matrices. So we are estimating 3 parameters. Each column becomes a parameter. When you estimate them, some of them will be significant, some of them might not be significant. Then you can update it as needed. Okay. It's a random parameter. So that's how the random parameter will be split. So you have beta k is split into mu k and sigma. So you're estimating mu and sigma from there. So if you have a normal random variable, when you take a realization, you will be able to generate the beta value. So if you have a mean, it will be simply mean plus sigma times is a random draw from normal, and you're multiplying it with the corresponding sigma. So I don't know if all of you remember this, how when we a normal distribution, this is how we standardize it. So now what I'm doing is I'm using this equation to find my x. So x will be mu plus g sigma, because I need the beta I need to use, right? So if a person has a mean of 2.5 and a standard deviation of 1, one possible value. Sorry, standard I can use it. So this will be the random variable that I draw, and then you will put 2 if that happens to be positive. Let's say the random variable is a normal random variable, let us say minus 1. Sigma is 1 here. So that will give me a realization of 1.5. Each time I draw a different z, I get a value. So anywhere, so the distribution would look something like this, around 2.5. So 1 point would be here, 1 point would be here, 1 point would be here, 1 point. We draw and then use that in distribution. For each value of beta, you get a different probability value. Okay, that has to be averaged. You cannot average the beta, you have to average the probability value. Okay? This is how the equation would look if you have multiple random. Each time you decide to have a random variable, you are integrating that term. So if you have 6 random variables, you are doing a 6-dimensional integral. So the higher the number of integrals, the lower will be of the integration. Okay, because you want to do a multivariate integration of 6 to 8 dimensions, it's reasonable. It is possible to do random numbers well, but if you go up to 12 and 13 or 15 and 16 random variable, the generating random numbers to compute without correlation becomes challenging. So because of that, the integral evaluation will get challenging and also time consuming. It takes a lot of time to evaluate these dimensions. So we don't call this process of estimation maximum likelihood because it's not a closed form formula. So we call it maximum simulated likelihood because we're actually simulating the log likelihood at different points in the function. Okay. Any questions? Okay. So for undergrad students, this is advanced. So if you're not fully following, that's okay. Just if you can get the gist of what we're doing, it should be okay. It's mainly targeted for the PhD students and the postgraduate students who are in the class. Okay. Because I cannot compute the function at every point on the distribution, that I would need to do infinite draws. So because we are simulating, so to avoid that, because that integral doesn't have a closed form. If you have an answer for the integral, then it would be maximum likelihood. Because I don't have any way to compute that integral, because it's an indifferent integral without solution, what I do is I simulate. So I take my range, so minus infinity plus infinity, and compute that evaluation at 100 points, 200 points, 400 points, or 800 points, and then take the average. So that is never an analytical solution, it's a simulated solution. It's not simulation like what we do in micro simulation, but it's a simulated because of the integral evaluation. But no, if you have to find a simulate an integral, just think about an integral computation. Okay, if you have to compute the area under the curve, if you have only one dimension, computing the area is very easy. If you have 2 dimensions, it's more hard. It's complex. Yes. So is volume easier to compute or area easier to compute? Yes, because it's a numerical term, right? When you have 3 terms, when you have 3 dimensions or 6 dimensions, the accuracy of if it's a numerical formula, there is a clear analytical formula, it will always be exact. But when you are trying to compute in space, okay? So if you have 2 dimensions like this, I have to take draws on this dimension and in this dimension. So I'll get points, right? So the number of draws required for evaluating a 1-dimensional integral versus a 2-dimensional integral, the need is much higher. When you have the 3rd dimension, it starts exploding. But we are telling we're keeping it 200, 400. We are not in proportion. If you proportionally keep increasing, it will take 3 days to run 1 iteration. Okay, so if you're keeping the number of draws the same, as dimensions increase, your accuracy again drops. As in, I'm not talking about the accuracy will be at the first decimal. No, I'm talking about the 4th or 5th decimal. It will drop because we have now computational power to handle it. But another challenge is, right? In reality, there is no random draw. Our draws are based on some process of pooling the system. So when you draw 2000 data points for 16 dimensions, the first 100 and the last 100 are likely to be correlated. So once you know this, you can detect. So when that happens, accuracy again drops. So there are ways to address that. There is shuffling and a lot of things that I'm not going into that you can do, but it's a lot of work. So I personally don't like to see models with 12 random parameters. I mean, you're doing something unnecessary. Because if your data has independent, you can get 12 random variables only when you're willingly dropping some independent variable. Okay, so in our models, in my group, we have not gotten more than 3 random variables significant in most specific, because we try every observed variable carefully. When you specify a very good observed model, there should not be so much unobserved heterogeneity unless you have a lot of missing information. If your data is such that you have a huge amount of missing information, yes, then you can get some random parameters. But even then, you cannot explain all the random parameters very easily. All you are telling is there is a distribution. Yes, it's nice to see the distribution, but it's not the same as the physical meaning of a systematic variable. So if you have beta coefficient, if you see a lot of random variability, think about interacting that beta with age or with income or with other variables. That will reduce your random variability in your system. So always try systematic components first, then only you should try. The process when you estimate models, you should not have to try 10 random parameters in your model. Okay. So now I'll quickly talk about the mixed logic equivalent in the ordered space. So we can have ordered models. So we talked about an ordered response model. Let me show the figure. So if you have an ordered model like this, you have 5 alternatives. So here these are injury severity alternatives. So no injury, possible injury, non-incapacitating, incapacitating, and fatal. So if you have these five categories, in an ordered response model, the curve can move. The curve can move to the right or the left. But in a generalized ordered response model, we can move these lines also. Okay, so if you move these lines along with the curve, that increases the flexibility you have in capturing coefficients. Now, just like an ordered a mixed logic model, here also the coefficients can be random. So the effect of a variable such as speed limit is positive on engine security. The higher the speed limit, higher is the crash. But in some locations, there might be some treatments that have been made to reduce the effect of crashes. So maybe they have barrier from the side, soft barrier from the side, and so on. So in those locations, even though speed limit is high, engine security is low, which means the effect of speed limit has been reduced because of other unknown treatments that are available in the data. So in that case, we can allow for a random parameter for the effect of speed limit, and so that it can be lower for some locations, higher for some locations following that distribution. So again, everything that we talked about in the mixed storage space is directly applicable in an ordered response model also, and we can modify an ordered response model to create what is called a mixed generalized ordered response model that allows for variation. So this would be how the standard model would look like. We talked about this. It's just beta x plus epsilon. Here I'm not using alpha, so I have an extra threshold instead of that. In these, the size are constants across the population. But when we go to mixed order logic models with generalized order logic models, I am parameterizing the threshold also. The threshold is written as threshold plus minus the previous threshold plus exponential of it. So let me explain this. The propensity. So when you have a random parameter in your threshold, okay. So because we can write propensity psi1 and psi2. We have three components here for three alternatives. So we can decide to make this 0. One of the three alternatives we make 0. Here you have alpha plus beta x, and here you have delta x. Okay. So you're changing the threshold with different independent variables. So now if you have an epsilon here, you can have random parameters inside this also. So what that means is this delta x has a beta and a sigma inside, or a beta, or we'll call it delta prime. So you have, okay. So what happens is when I have a random drop, psi2, if I leave these two free, psi2 can become negative. What that means, because I'm using a normal distributional assumption, when I take one realization, but again, rarely, psi2 can become smaller than psi1 if you leave it as a free variable. Because when here this is 0, this is always 0. Because of the random variable, any independent variable that we have, psi2 can actually become less than 0. So we don't want to let that happen, because that would violate the ordering of the thresholds. So I think Dr. Karthik Srinivasan has a paper where what he did was he checked each time he take a drop in 2002, if I remember correctly. So he would check whether it's going less than 0. If it did, he dropped that realization and kept repeating the process. Now that is very time consuming, because we have to you cannot run the code freely. You are at each iteration, for each realization, you are checking, and then if it goes to less than 0, you again draw one more to make sure it happens. And there's a problem, because if you continuously draw all of them at once, you're drawing uniformly. There's no bias that you're introducing. But if you start eliminating some of them, you are not keeping everything for equal probability. So that creates an issue in the estimation process. So what we did here is we actually changed how the thresholds work. So what we did was we said psi1 is equal to 0. Psi2 will be psi1 plus exponential of delta x. So similarly, psi3 will be psi2 plus exponential of delta x. You can get any negative value in this equation. Psi 2 will still be more than psi. Similarly, psi 3 will always be more than. If you do with this parameterization, we don't have any issue with checking whether what I'm getting is negative or not. So that's why you'll see the exponential here. So this will make the estimation process a little complicated because you have to take the derivative of the threshold. So when you take the derivative with exponential, it's harder than when you don't have that exponential. But we were able to do it, and this is the probability that comes through. So this formulation of the generalized ordered logic model ensures that even in the space of random parameters, you won't have threshold ordering issues. Okay, so this is what we used in my 2008 paper. So I have a case study on this. I'll quickly go show only the interesting things. So this is a paper in accident analysis and prevention. So what we did here was we looked at pedestrian and bicyclist fatalities. Okay, so we had about 4,800 pedestrian. This is just a motivation. You all know why it is important to look at pedestrian. I'm not going to talk about that. So I'll get to the data. So this is the data that we used. So we wanted to differentiate between pedestrians and bicyclists because the injury profiles are different. You'll see the chance of fatal injury for pedestrians is much higher than bicyclists. Similarly, if you look at non-incapacitating injury, you see a higher share for bicyclists. So bicyclists survive better because at least they have a bike to prevent when a collision happens. Still, it's high. Same thing, you'll see that incapacitating injury is also much higher for pedestrians. Fatal injury is also much higher. So we looked at different independent variables here. So here I am looking at the effect of non-motorist being intoxicated. Okay, non-motorist consumes alcohol. You'll see a significant change in the percentage profile. So you'll see that they are likely to survive with a higher probability if they don't use alcohol. The probability for fatality increases. Not just fatality, this reduces, this increases, this increases. So the curve, the injury severity spectrum shifts downward. So basically, non-incapacitating is it's not like you lose your leg or hand. It is severe. You broke your hand, but you can you put a fracture and it will come back to normal. But incapacitating means they had to amputate something. It's a severe, basically much more severe injury. So in this model, we were able to estimate, we have 4 alternatives. So we were able to estimate 3 equations. So there's a latent propensity equation, which is general to everything. Then we have the thresholds, the last 2 thresholds for what were estimated. The first threshold was set to 0. So here, so again, you will see that in this model, we did not get any random parameters. Again, because we have so many independent variables, nothing came significant other than our independent variables. Okay. So we can see some of the variables we try: age, under the influence of alcohol. So positive means the injury severity will increase in this column. Negative would mean injury severity will decrease. So you'll see if the collision is with the SUV, you get a severe injury. And with pickup truck, the full profile doesn't shift, but the thresholds shift. So the last 2 thresholds shift to the left, so increasing the probability. So pickup truck does not, if the bicyclist or a pedestrian collides with the pickup truck, it does not change the probability for the first 2 alternatives, but it changes for the other 3 alternatives. So again, the nonlinearity in the thresholds allows you to carry such interesting relationship. So sports utility vehicle moves the entire profile to the right, but the pickup truck variable, it only moves the last 2 alternatives to the left. So it changes, so probability increases for that. Same thing for van increases the fatality probability. Also, we tried roadway characteristics, accident location, environmental factors, and so on. So here we are comparing our model to the observed data and also with a standard or order response model. So what we are doing is we are looking at the shares, prediction shares These are the actual shapes. The first column is the actual shape, and you can see that the ORL model comes close, but not as close as the MGORL model. You see the MGORL model does a much better job. You can check the root mean square error and mean absolute percentage error is substantially better for MGORL model, both for pedestrians and bikes. So it substantially improves the data fit in this. So again, in the interest of time, I don't want to talk too much about that. So, but again, that paper is the most cited paper in my research career, and you can download it from my website or attend if you're interested in it. Okay. So now, what I'll do is I'll start talking about the machine learning approaches. So again, as all of you know, machine learning originated as a branch of computer science and also grew out of AI. So there are different problems that are looked at in the machine learning as well. So it teaches computers how to solve a problem by example, right? So one of the things you can think about is vision. Computer vision is a very common application where you pass several images of cars, and then actually I think they start with dogs. They show images of dogs and see if a random image is shown, it can it recognize it as a dog or not, or an animal. So now we're using it in transportation to identify pedestrians, cars, or bicycles, and so on. So it depends on how good your training data set. If your data set is good, it can help in that. So just like we use statistical models or econometric models, machine learning models are also used for similar problems. You can look at classification, where you are trying to predict yes or no, or 1, 2, 3, 4 categories. So categorical responses is defined as classification. Regression is what we are doing as regression, right? So you want to predict number of vehicles on the road, or traffic safety issues, such as number of collisions that will happen on a particular facility, and so on. That will be captured as regression. So clustering is slightly different. So clustering is you are trying to group similar objects. So what we are trying to do is there is no this is group 1, group 2, group 3. You just are given a bunch of items, and then looking at the characteristics and features of these items, you are grouping them into, okay, this set of records look similar. They should be cluster 1. This set of records look similar, so they become cluster 2. They become cluster 3. So these 3. So you minimize differences across entities within a cluster. So similar items that are similar to one another should fall into one group. There are ways of doing that. So these are the 3 techniques we'll talk. There are a lot of methods to do each of these. So we'll discuss those as we go. Okay. Any questions? Again, I don't work in machine learning per se, because for me, until I can see the mathematical formulation in fullest detail, I don't do research on those items. So I have collaborators who work on it. These slides are materials that I got from another colleague who works exclusively in machine learning. Right? My colleague at UCF, Samuel Hassan, he works in machine learning a lot more. I use these as a way to check how my models are doing, but I don't do search in these topics. So if you look at a classification problem, so what we're doing there, we're trying to figure out, so you have a training of observations, and whenever you do machine learning, there are I think 3 phases. Right? You have training part, testing part, and testing part. So that's the important process. So you train your data and test it to make sure it's working, and then validate it. There is cross validation approach, different ways of doing that, but that is the main focus. So here you have each observation is represented by features. You call them features or whatever numbers you have. Right? So if you look at an intersection, if it has a severe crash or not, is the variable that we're looking at. This is the variable we want to classify. So we are trying to answer, will this intersection have a severe crash or not in the next year? Okay, so that is the classification variable we're interested in. Now we will look at all the features. So what should it depend? It should depend on average traffic per hour or per day, average cycle length, because it's an intersection. We are looking at queue length, whether the signal is the signal design is adaptive or not. Again, this is in the US context, so right turn is free there. So that's what we have. So we have this information. So what it does is it takes these features of numbers and tries to classify based on different data sets. Right? It looks at there are a series of records like this. So it's not just one record. We'll provide probably 1,000 intersections or 2,000 intersections, and based on this, it will start associating. Okay, when traffic flow is higher, severe crashes might not, or when the average queue length is high, maybe severe crashes happen or not happen. So things like that. So based on that, we will start associating probabilities for the crash to intersection to have a crash. So here the functions do not necessarily look easy to see. In a multinomial logic model, I can tell you what the utility is, the expression is very clear. But here it becomes, there are so many layers of these functions that trying to interpret that functions might not be very useful. You are just looking for, okay, what is the prediction? So let's use that prediction as an output and see what happens. So here the training set is 2015 and before, testing set is from 2016 to 17. So you train the data, everything before 2015, test it with 2016 to 2017, and then in 2018 you're predicting whether a crash, severe crash will happen or not. Okay, that is the process we typically use in a classification. So one approach to look at how to do this is you're trying to, whenever you're trying this classification, you have an implicit function, right? Which is called, let's call it f of x for standard here. So this f of x is a function of a lot of independent features that you are providing to your model. What it's trying to do is it's going to say, okay, there is a boundary. I call that f of x is equal to 0. If f of x is greater than 0, there will be a crash. If f of x is less than 0, there won't be a crash. Okay. So that f of x need not be a linear function. It can be very non-linear function. So it's again similar to what we do in our traditional discrete choice models. Right? So there also we are estimating a propensity, and if that propensity crosses a threshold, we say that the event will have a crash, the system will have a crash or not. Here, what we are doing is we are doing it in a function similar structure, but that function has multiple layers embedded within it. That way, it's more complicated and can be customized to the data much more than what a discrete choice model will do. And so the number of parameters that go into this computation also will be large. They're using parameters to get better accuracy for the data set that they're looking at. So there are different classification algorithms. Again, some of you might have seen. So logistic regression is nothing but binary logic. Okay, so it's the same logistic regression. There are decision trees, support vector machines, random forests, and neural networks. So all of these use different ways of capturing the same. So their objective is very clear. It is how do I increase my predictive ability? So if you run a good logistic model, maybe you get an accuracy of 70%. Okay. So if you go into decision tree, the objective is how can I make that 70 go up to 80 or 85. Same thing with SVM and other approaches. We are simply figuring out ways to add additional parameters to improve accuracy. So I think there is value in adding these parameters. So at some point they'll increase, but there is a chance that you are adding so many additional parameters, you are overfitting the data to your context. So when you take it and use it on a data set that is not being seen before, they might. Okay, again, it's not necessary, but that is a major issue with machine learning models. Machine learning models are known to do very well on data they are trained for. But if you transfer it to another data set, will the accuracy transfer or not is the biggest question you need to be answering when you're using machine learning. So in some cases they will, okay, which is good because if your parameters are not overfitted, when you use it for a new context also, they do well. But you always have to be wary of it not doing well in an untested data set. No, so but here classification is always supervised because you know what the classification is, right? Yeah. So no, the problems that of overfitting will go to any application. If whether it's unsupervised or right, even in unsupervised, because it wants to cluster them very well, it'll add too many parameters, it'll add a lot of parameters. So when you translate the context, that parameter parameter space might not translate to a new data set. So we have 3 clusters in a data set that you. So when you bring in a different city and a different data set, maybe we don't need 3, we only need 2, or maybe there are 4. So in that case, it will try to fit all of them into the 3 because that's what it's trained. So that problem will translate anyway. Okay, because if you look at behavioral models, the number of parameters are very small, like compared to number of data. We have 2000 data points in any of the models that we do. You go up to 100 parameters, maybe 150. Here you go up to 1000, 1500. So what happens is when you have that many parameters, you are putting one parameter per data point. So you will improve accuracy there. Again, it's not, but when you take it and use it in a data set that is never seen, those parameters might not work as well. Okay, but this is not to criticize. There are ways you can test that and then apply it so that you don't make that mistake. That's not an issue. There are ways to check. So again, I am not going into mathematical details of all of these. I'll show a little bit about some of these models as we go forward. So in regression, so classification is you're separating items. In regression, what you're doing is you're actually talking about how many pedestrian crashes will occur in a given intersection. So coming up with the numbers. What is the traffic? How many cars? How many people will. So again, this is a continuous number. You are trying to get to using regression approaches. So here we are not classifying it into 1 or 2 groups, but we are actually trying to predict the number of values. So here the change from the previous classification problem is there we were only focused on will a crash happen or not. Here we are actually predicting the number of crashes. So your output here is not an yes or no question or not 1, 2, 3, 4. Here it's actually the number. So it could be 5, it could be 250, it could be 400. So you're trying to get to that. So if you are giving a function and you are given number of crashes and function of flow, so because there is a lot of flexibility, we might be fitting it in this way. So this way, if you fit it this way, you're getting 0 error pretty much for the entire data set, right? So because the curve can go, when we do a linear regression, what do you just draw a single line through all of it, right? So it would look like this. So this obviously has a lot of error because we are only passing a linear line which is not covering everything. But the previous case, basically what it did is it determined where to turn. At each point, it added a parameter recognizing the slope as change. So this is an example of a model that is overfitting the data. Right? Yes, your error is 0. But if you use new data set, new crash data, it won't predict very well because it's randomly turning up and down everywhere. Okay? So now we want to add flexibility. Right? We don't want to use linear regression only because linear regression is very restrictive. So we can look for some nonlinear approach which takes the relationship better, but not by overforce. So here all we are doing is we are kind of identifying a parabolic structure that represents good accuracy with our model. Okay? So this will not have accuracy of 100%, but this is a more representative data. So what we are showing here is as traffic flow increases in the beginning, crashes increase a lot, but after a point it tapers down. Right? This is something we can explain, and this is more likely to be transferable to multiple locations than a system that overfits the data. So there's always this question of how much accuracy you want on your training data, right? So if your objective is to get 99.99% accuracy, you will be doing a model like this, right? Where everything is fitted to the data like that. But our objective is not for training data. Our objective is how do I make my model work on my outside data set, right? Or a validation data set, because that is where I want to use. I already have the data. I already know how many crashes are happening in different locations. So I don't need a model to fit that perfectly because I have that information. What I need is for it to predict in a different context to show me what the crashes will be. So if I build a model that is overfitting the data, I know that I do a very good job on the training data set, but do a lousy job on the validation data. So I don't want to do that. So what I want to do is I need to keep my expectations focused on the validation data set that we want to use. Okay? Don't try to do the perfect job with your training data. If you do that, it will be great for the training data set to show your numbers. But the moment you apply that model with outside data, it will significantly underperform. Okay? So at the same time, I'm not suggesting use linear regression and do it, right? We're not suggesting. All we're suggesting is find the right balance. To find the balance where you find something like this, where there is error, but this is an error I can live with because I know it works well here and it should work well on the validation data set also because we are actually reflecting behavior in terms of how the relationship between number of crashes and traffic flow should look like. No, this is an example in a two-dimensional space. It's not like our models are only, there's only one feature and one dependent variable, right? We have one dependent variable and you could have 20 independent variables. So we want to come up with something smooth like this across all. So if you can imagine this one, just like we fit these two, even when you have 20 dimensions, you could fit to each answer across all 20 dimensions. Right? So that's where the number of parameters start ballooning very fast in a machine learning model. So you need to be careful in determining how many parameters you want to add to improve your accuracy. So just like we looked at an example where the R square value increased 0.5 per 6 parameter, 0.52 per 100 parameters. And we said we don't want that 100 parameter model because even though it has a higher R square, it is clearly overfitting the data. Same thing, there are ways to check for that. There are different approaches that specifically focus on are we overfitting, the data can be generated to check if they are overfitting, and then you can correct for that in your models. So, as we talked about, there are two mechanisms of how these models are developed in the machine learning world. One of them is called supervised learning. Supervised learning approaches are defined to cases where we know what the dependent variable is. Okay, so every model, every transportation data set that we have talked about is effectively supervised learning because we know the dependent variable, we know the mode choice, we know the number of crashes, all of that data is available. So in some cases, we won't have those labels. Those are what are referred to as unsupervised learning. We will talk about that. So classification and regression are supervised learning problems because there is a clear label associated with every. So in machine learning, usually they are labeled as +1 or -1. And numerical, regression also has numerical labels because you know the number of cars or number of crashes or whatever is the dependent variable that you use. Okay? So supervised learning algorithms are much easier to evaluate because we have the ground truth, right? So the benchmark is available because you can always say this is the observed model. Unsupervised get tricky because there is nothing to compare because we are creating the groups, but there is no answer saying, oh, these are the groups hidden in the population. We don't know that, right? But in a supervised, so for that reason, it's actually easier to develop models and also evaluate them in the supervised space compared to the unsupervised space. So what we are doing here is we start with this process where we are looking at the data. We have to pre-process the data to make sure appropriately, and we might have to do some transformation. So basically, some text, if it is available, we'll have to convert that into numerical data. Then once we have the transformed data, we look at applying the different approaches. So any form of supervised learning or unsupervised learning. Then we are looking at interpretation, so we can see the patterns. And again, the end goal is not just to come up with a high prediction model. Our end goal is to draw knowledge from it, right? When machine learning models start coming up, they entirely focus on purely on prediction, accuracy, and so on. But now they also are starting to do emphasis on, okay, what are the important features? So can I rank them? Can I provide information on which feature is the most important in my data set, which is the next and also the Sharp evaluation, where they're trying to interpret some of these impacts of the various variables. So the main objective would be to convert what you find from your analysis into knowledge, so that we can influence practice or research and application. So another thing that we need to think about when we're doing analysis with large data sets is how do you plot that data, right? So if you first thing that you do whenever you get data is before building models, you need to do some plotting of the data. So there are different ways of plotting some of these data. So I'll show you some. Here we are plotting speed versus volume. Again, this is just a scatter, right? Every observation is available. This is very easy to do. You can do matrices here by different independent ways. So you're looking at occupancy, speed, occupancy, volume, and this is just the frequency. So again, we actually have a plot that uses information from all dimensions. You can do it this way. Again, this is the line plot where all you're doing is you're trying to come up with a regression line for your data, right? So you plotted the relationship between occupancy and volume, and you can do this in Excel, right? So you can just ask for a line to be added to your chart. So you'll see what is the angle at which the data is moving forward as a function of volume and occupancy. A simple. Again, all of you know about the bar plot, so we are just looking at the distribution of speed across different days here. You can also have them identify the 95th percentile or the 90th percentile values as what based on what you want to show. This is a simple histogram showing the volume range across as a function of we're showing the probability here. So the whole thing should add up to 1. We're just showing where is the distribution of a particular volume.
Utility that an absolute thing doesn't matter. You are creating a value and it's actually related.
Yes.
So the utility part of the formula that was the data directly transferred.
No, because it's estimated purely based on the observed value.
We are creating the output basically.
No, it is unsupervised if you do a kind of a latent classifier where you tell there is a segment, but nobody sees that segment. That is unsupervised.
So the way actually it is only because we are actually looking at naming and finding something which is not
exactly. But those where if you cannot associate and you have to come up with a name, that is unsupervised. That would be the definition. This is another way of showing the data. So box plot. So this would be the significant distribution is available here. This is the upper limit and lower limit. This is the median of the data. So this could be 95 percentile or the median. So there are some outliers here. So this is a very nice way of showing, especially when you compare two models and predict outputs from there. You can see that in different models, the prediction changes across different data sets. So if you take multiple samples, the predictive power of all of them will not be exactly the same. So we use this box plot kind of approaches to show how good two models are. When you're comparing two models, it's not necessary that if you run it 50 times, model A will outperform model B all 50 times. But if you plot something like this, you can actually see how many times it's outperforming and also by how much, right? That is more important. So if a model loses once in a comparison, yes, that's bad. But you also have to focus on what happens the 49 other times that we compare. So a box plot does a good job of showing. And the volume plot is also very similar to the box plot. It represents where the data is, but it also shows the distribution of the data on that point. So you see that there's a lot of, on Friday, there's high volume of vehicles at 60 compared to, so in a box plot, we just show evenly. Here we are also giving extra information saying that this appears more. So similarly here, if you look at it, this record appears more than this record. We know that based on the width of the violin bar and that. So the length shows you the range of all the values that are used. So this is a nicer way of showing the distribution, as you can see. Okay? This is a whatever QQ plot. So you're just looking at what else that you have theoretically, and then what are the values you obtain, and then you have a regression line showing how the relationship. It is a different ways of plotting different kinds of data. You can choose to use some of these when you are running your models, because again, you don't want to be using very traditional models only. Sometimes these approaches will offer more insight for your data when you're processing the data. Any question? So let's get into some of these approaches. So logistic regression is already I'll talk about the case. So the idea of the k neighbor is that, so if you set k is equal to 1, okay, so what you are doing is you say you'll find the closest one and you take the choice of the other one. Okay, so basically what you're saying is your behavior is based on your neighbor. So it could be 1 if k is 1. If you take k is 2, based on behavior of the other you can put k can be 3, 4, 5. Again, the larger the k, the more neighbors you have to work with, so that can become a little more complex. What we think is using k equal to 2, so you only look at pairs. So and these are zeros and these are ones. So and this you are training and a test. So you based on what you know, you predict the other source. They are closer to that one. They are also following the same choice. So you optimize. You keep running it multiple times until you end up with class. You can try with k equal to 1 and see how it works. K equal to 2 and so you will see that you will start with the benefit will drop optimal k selection. Okay. So